You know the premise. A hypothetical cat is placed inside a sealed box. Until someone opens the lid to look inside, the animal exists in a state of suspended reality, vibrating between two completely contradictory states. It is literally alive and dead at the exact same time. Erwin Schrödinger, the Austrian physicist who invented this scenario in 1935, thought the entire concept was ridiculous. At the time, the scientific community was rallying around a Copenhagen interpretation of quantum mechanics. This framework argued that subatomic particles do not have fixed properties. Instead, they exist in a blurry, probabilistic superposition until they are directly observed, at which point they lock into a single state. Albert Einstein firmly rejected this blurry version of reality. In letters to Schrödinger, he pointed out that physical logic has to hold up. A keg of gunpowder, Einstein argued, cannot be exploded and unexploded at the exact same time. The universe has already decided what happened long before you look at it. Schrödinger agreed. He allied with Einstein to publish a paper specifically designed to expose what happens when you take the rules governing subatomic particles and scale them up to the size of everyday objects. The most famous thought experiment in science was originally forged as a weapon. Schrödinger intended to destroy the exact theory his cat is now famous for explaining. To build his trap, Schrödinger laid out a precise physical system. He imagined penning a cat inside a completely sealed steel chamber, isolated from the outside world. Next to the cat, he placed a tiny amount of a radioactive substance and a Geiger counter. These components are linked to a relay. If the Geiger counter detects the decay of a single atom, it releases a suspended mechanical hammer. That hammer then drops, shattering a small flask of hydrocyanic acid and killing the cat. Over the course of an hour, there is exactly a 50% chance that the atom decays. Under the Copenhagen rules, until the atom is observed, it is both decayed and intact. Because the atom state determines the mechanism state, the hammer is simultaneously dropped and suspended. The cat is alive and dead. Schrödinger used this logical chain to corner his colleagues. Without a clear mechanical boundary defining where quantum rules stop and classical physics takes over, their theory resulted in a physical impossibility. This contradiction exposed a massive hole in physics, known as the measurement problem. The microscopic world operates under a set of rules that completely fall apart when applied to the macroscopic world we actually experience. As the modern physicist and Nobel laureate Roger Penrose points out, a cat-sized object existing in two states at once is a physical absurdity. Massive objects simply do not behave this way in reality. The original Copenhagen interpretation tried to bypass this by giving human consciousness a mystical power. It suggested that the act of observation by a conscious mind forces a wave function to collapse into a single, solid reality. Schrödinger's thought experiment successfully highlighted the absurdity of a magical human observer. It forced the scientific community to search for the actual mechanical bridge between the blurry subatomic realm and our solid, predictable reality. In 1957, physicist Hugh Everett proposed a radical mathematical solution to this problem, which later became known as the many worlds interpretation. Everett argued that the wave function never collapses at all. Instead, the universe splits. Every quantum event acts as a branch point, creating one isolated, fully real timeline with a dead cat, and an equally real parallel timeline with a live one. While many worlds has its defenders, a more mainstream mechanical solution eventually emerged: decoherence. Decoherence removes the human mind from the equation completely. Quantum states are incredibly fragile. To maintain a superposition, a particle must be perfectly isolated. The observer breaking this state doesn't need to be conscious, it just has to be the surrounding environment. The moment the atom interacts with the Geiger counter, the box, or an air molecule, it settles into a definite state instantly. A macroscopic cat is never actually dead and alive. The environment inside the box interacts with the atom constantly, resolving the quantum state long before a human ever opens the lid. While macroscopic objects like cats cannot enter superpositions, modern physicists at institutions like Oxford use these exact principles to manipulate the microscopic world. They routinely create what are now literally called cat states in the laboratory. Using quantum harmonic oscillators, scientists place light, vibrations, or trapped particles into multiple states at once, creating wave packets that move in opposite directions simultaneously. This ability to isolate and control dual realities is the foundational engineering behind the qubit, the engine driving quantum computing. Inside highly specialized environments, like the dilution refrigerators shown here, systems are forced to exist as a 0 and a 1 simultaneously. This overlapping state allows the computer to process vast amounts of calculations at once, vastly outperforming the linear processing of classical binary computers. Schrödinger designed his trapped cat to demonstrate that quantum mechanics was physically illogical. By isolating that exact illogical behavior, scientists discovered the precise blueprint needed to harness the computational power of the universe.